Hi everyone. In this video, I will be talking about how to test a second order factor analysis using Stata. And what you see on your screen right here is just a visual representation of the main model that we will be testing. So as we go through the video presentation, I'm going to start off by just kind of talking through a few concepts and kind of revisiting a little bit on confirmatory factor analysis, and then distinguishing between a first order factor model and a second order factor model. And then we'll open up Stata and we will specify both a first order factor model and a second order factor model. We'll talk through some of the results, and then we will test the difference in fit between those two models. So we'll go ahead and start off just by talking a little bit about the difference between a first order factor model and a second order factor model. So if you look on your screen, you'll see on the left we have basically a first order confirmatory factor analysis model. And in this model, you'll notice that we have our latent variables, which are denoted with the ovals that you see right here. So basically, these are proposed factors associated with a measure of coping styles. So we have a problem-solving factor, cognitive restructuring factor, express emotion factor, and a social support factor. And the rectangles that you see over here, these are the measured variables, or basically the variables that we have data on associated with each of the individual items in the questionnaire or survey. And so what we have right here are three items that are proposed as indicators of problem solving. So it's basically these three items right here. Then we have three items that are proposed as indicators of cognitive restructuring, three that are proposed as indicators of express emotion, and then three that are proposed as indicators of social support right there. And you'll notice that we have our arrows pointing from the latent variables to the proposed indicators, and the reason why is because each of these factors are essentially proposed to account for the interrelationships among those particular indicators. And so you'll notice that I've got the names of the indicators as P1, P2, P3 for problem solving, C1, C2, C3 for cognitive restructuring, E1 through E3 for express emotion, and S1 through S3 for social support. And so with the arrows pointing to those variables right there, the idea is that the variation, or at least part of the variation in each of those indicator variables, is accounted for by that latent factor. So in other words, the indicators are proposed to are essentially treated as reflections of their respective latent factor. So that's the reason why we would call it a reflective measurement model, is that the indicators are reflecting a construct. So with those arrows pointing from the latent constructs to the indicators, you'll see that again the latent factors are proposed to account for some of the variation in those items, hopefully a good bit. Then also you'll see on the left side of these indicator variables, we've got these circles with the arrows drawn to them with little epsilon values in this diagram right here, and those are what are referred to as uniqueness. So each item has a uniqueness, and that's essentially measurement error. And part of that measurement error is going to be unreliable variation. Essentially, part of the variation in each of these indicators is going to reflect unreliable variation, as well as perhaps some systematic variation that's specific to those items. But when I say systematic, basically something that has not been modeled as a system, as accounting systematically for variation in these items. So there may be other factors outside of these factors that we have in our model that could also account for some of the systematic variation in those items. So as you can see right here, each item then, the variation is accounted for by the latent factor, or its respective latent factor, as well as variation that's unaccounted for, part of that variation being unreliable variation, and part of that variation being basically kind of more specific systematic variation associated with that particular variable. It's just unmodeled. So as we're looking at this model too, you'll notice that I've got these paths right here, these are all fixed to 1. And the reason why we have this in our model is to set a measurement scale for the latent factors. So if we don't have a measurement scale for those latent factors, then what will happen is that the model will become unidentified, and then basically it's not going to work when we try to run our analysis. So one strategy is to set the measurement scale of those latent factors in relation to a marker variable. And so you'll notice right here that basically we've got P1 as being a marker variable, C1 right here, E1, and S1 right there. So we're setting the measurement scale of our latent factors in relation to those marker variables. We might also think about them as kind of reference indicators. But at any rate, the other strategy that is possible is to, instead of fixing those factor loadings to 1, we could just fix the variances of the latent variables to 1. And in that case, we would not have those fixed factor loadings, and then we would be estimating all of the factor loadings. But when we have the imposition of that fixed factor loading to 1, then we're not estimating those paths. Those are just those are givens, and then the remaining paths, or in this case our factor loadings, all those would be estimated. You'll also notice too with our factor model that we have double-headed arrows pointing between each of the latent factors. The double-headed arrows signal covariances between them. So we have all possible covariances among those latent factors that are specified within this model. Now, when we look at the model on the right, this is our second order CFA model. And you'll notice that in terms of the relationships between the latent factors, the first order factors, if you will, and the indicator variables, and then also the error terms, all those look exactly the same as what we've just talked about. But now we're adding in second order factors into the model. And the reason why is because we may have some reason to suspect that we can account for the correlations among the first order factors, these correlations down here, with second order factors. So in this case, we're trying to account for the intercorrelations among the first order factors by proposing second order factors. And so within this model right here, you'll see that we've got 2 second order factors specified. We have problem focused coping and emotion focused coping right here. And you'll notice that we have arrows, single-headed arrows drawn from each of those second order factors to the first order factors over here. But in this case, we're specifying that problem solving and cognitive restructuring, that the correlation between those 2 first order factors can be accounted for by the problem focused factor. And then in terms of express emotion and social support down here, we are proposing that their first order correlation is accounted for by the emotion focused factor, the second order factor over here. As you can see, in terms of the structural portion of the model, you can see that I have ones for these 2 factor loadings right here. And basically, again, we have to set a measurement scale for those second order factors. So one way that we can do that is by fixing a given loading to 1 for each second order factor, or we could just estimate those loadings separately, and by virtue of fixing that our second order factor variances to 1. So we can do it either way. But nevertheless, given that we have arrows pointing from our second order factors to the first order factors, now we can say that part of the variation in those first order factors is going to still be unaccounted for by those proposed second order factors. And that's why we have our error terms associated with each of these first order latent factors. Okay, so the other thing to note too is that as we're looking at our model right here, you can see that I've got correlated second order factors that are being represented by that double-headed arrow. Now, as we're looking at these two models, the first order factor model and the second order factor model, you might not necessarily think to look at it, but believe it or not, the second order factor model would be considered a more parsimonious representation of the interrelationships among those indicator variables than the first order factor model. And we can kind of make that determination by counting the number of parameters and also the degrees of freedom for the model. So just briefly, the degrees of freedom for a model, for the full model, is basically just counted by taking the number of indicator variables that we have and essentially multiplying it by the number of indicators plus 1 divided by 2 right there. And then essentially taking this number right here and subtracting the number of free parameters in the model. So I'll just say number of free parameters right here. Okay, so if we want to just kind of do this really quickly, you'll notice that the model on the left over here, both models have 12 indicator variables. So in terms of the this part of the expression right here, this part of our equation right here, this is counting up the number of unique or distinct elements within the variance covariance matrix of the indicator variables. So essentially we have 12 indicator variables in our model. So if I just multiply that by p plus 1, that would be 13 right there, and then divide by 2, that gives us 78 unique elements within the variance covariance matrix for those indicator variables. And in terms of the number of free parameters that are being estimated, we can count them up in the following way. We have 12 measurement errors or uniqueness values or uniquenesses associated with those indicator variables, and so the variances for the measurement errors is going to be 12. So we have 12 measurement error variances that are specified right there. Then we also have now, because we have the fixed parameters right here, here, and here, those loadings are not going to be estimated. So the remaining factor loadings will be estimated. So we have 1, 2, 3, 4, 5, 6, 7, 8 of those factor loadings that are going to be estimated. All right, so now we're up to 20 free parameters. And then we have the variances and covariances for the latent factors, and we can actually count that up very similar to what we had done above with the indicator variables, because we would have a variance covariance matrix of those latent factors. So I'll just call the number of latent factors k, so I'll just say k plus 1, and then divide by 2. So we have 4 latent factors, and then so basically 4 times 5, that's 20, divided by 2, that's going to give us 10 additional parameters right there. So when we add all of these up, that will give us, basically, it'll give us 30 free parameters within the model. So that's the number of parameters right there. So if I take the 78 for our degrees of freedom, the 78 unique elements or distinct elements within the covariance matrix, and subtract the 30 free parameters, that's going to give us 48 degrees of freedom for this particular model. Now, in terms of the model on the right, the second order factor model, basically we still have the 12 measurement errors, and we still have the 8 factor loadings that are being estimated within the first order portion of our model. So we still have our 12 parameters, we have our 8 parameters, and then as we look at it, you'll notice that we have the error terms associated with each of those latent factors. So in that case, there's 4 additional parameters that are estimated right there. And then we have the variances and covariances involving the second order factors. So we have 3 additional parameters because we have a variance estimate associated with our problem-focused variable and emotion-focused coping variable right there, and the covariance between them right there. So we have 3 additional free parameters, plus we have this loading here and this loading here. So there's 2 additional ones right there. So then the total number of estimated parameters in the model is going to be 29. Okay, and so if I take the degrees of freedom for the model, it's just basically our 78 minus 29, and that will give us, then in this particular case, it will give us 49 degrees of freedom. Okay, so as you can see, because we have fewer parameters that are estimated in our second order factor model, that would actually be a more parsimonious model theoretically than our first order factor model. And ultimately, once we've run these two models using Stata and we assess their fit, we can calculate a chi-square goodness of fit value, test value for each of those models. We can actually compare the models using a chi-square difference test, with the degrees of freedom for that difference test being the difference in degrees of freedom between these two models. So now let's go ahead and open up Stata and run our analysis. So at this point, we've got Stata open and we're going to run our analysis. But before we do that, let me just kind of highlight that we have our variables and our data already in Stata. It's actually using a summary format, but these are the our variables right here, or at least a subset of them. Obviously, you can kind of scroll down and get a little bit more. But as you look at the raw, well, not our raw data, or summary data, if you kind of go into the data editor right here, you can see it's in summary form right there. And you can download a copy of this data by following the link that's provided underneath the video description. So what we'll do now is we're going to open up the SEM builder. So I'm going to go down here to SEM, structural equation modeling, click on model building and estimation. So I'll click on that, and we get our SEM builder, and basically you just specify, we're going to specify first our first order factor model. We'll test that out, and then we'll specify our second order factor model and then test that out, and then we will compare the two using the chi-square difference test. So what I'll do is go ahead and kind of set the canvas here. Actually, I'm just kind of straightening things up just a little bit to give me a little bit more drawing space to work with. And, over here on the left, you'll see you've got the boxes for observed variables. You've got the ovals for add latent variables, and our single-headed arrows for pass, double-headed arrows for covariances. So what I'm going to do at this point, I'm going to make the assumption that you already know how to work with this builder at this point. And what I'll do is I'm going to pause it and build the first order model, and then we'll kind of go through it, and then we will proceed to the second order factor model. Okay, so here we have our model drawn up using the SEM builder, and it's literally the same thing that I was showing you just a couple of seconds ago. So again, we have our latent variables, our first order factors with arrows drawn to their respective indicator variables. We have our marker variables with the factor loadings for those being fixed to 1, and obviously you can see the uniquenesses in the model, as well as the correlations among the factors. So what we'll do at this point is we're going to estimate our model. We'll click on estimate right here, and we'll go ahead and stick with maximum likelihood, which is our default right here. And when I click on OK, basically you'll see that these are all unstandardized estimates within the model. So the double-headed arrows that are linking our factors, the values associated with those are covariances between those factors. Then we have unstandardized factor loadings and so forth. We can go into the main part of our output right here, and you'll see that we have in this column right here, this column in terms of the measurement portion of our model, you can see that we have the fixed loadings of 1 for each of our marker variables, and then the remaining loadings are all estimated. So these are the unstandardized factor loadings in our first order model, and you can see that we have significance tests associated with those. So there's no significance tests associated with the fixed loading. So it's only for those factor loadings that have been estimated within our model. So you can see, basically, if you kind of scroll down, you'll find that all of the unstandardized factor loadings are statistically significant. Scrolling down a little bit further, you'll see that we have the variance estimates associated with our uniquenesses. And so that's what all of these are. Then you have the variance estimates associated with the measurement errors for the first order factors, which are, down here, as you can see down here. Then finally, if you look down this portion, you've got the covariances among the latent factors as well as significance levels. Now, oftentimes when people are running factor analysis, they prefer to report on a standardized solution. So we can generate that very easily as well. So what I'll do is I'm going to go back to my diagram right here, and under SEM Builder, we'll click on Estimate. We'll go to Reporting and click on Standardized Coefficients and Values. So when I click on OK right here, now we have the standardized estimate. So the double-headed arrows, the values associated with those are now correlations among those first order factors. Then you'll notice that we have our factor loadings, all of them, all the standardized loadings are estimated. And the reason why is because now with this particular solution, the latent factors, all of them have a variance that's fixed to 1. That's why you see a little 1 appear in there. So all of the estimates, including what we had for the all of the loadings, including the one that we previously had for our marker variables, all of those are estimated. So you'll see here, we've got our 3 loadings right here, 3 loadings right here, and so forth. And all of those in this model are going to be correlations between the indicator variables and those latent factors. And if we go into our main output, you'll see that now the estimates are standardized for fully standardized solution. So we have the coefficients. These are the factor loadings. So these are the standardized factor loadings. Like this one right here is the standardized factor loading between problem solving factor and P1, then problem solving and P2, and then problem solving and P3. Keep in mind that the factor, when we specify those arrows pointing from the latent factor to the indicator variables, the idea is that the variation in the indicators is being accounted for by the factor. So you could kind of think about the latent factors as essentially independent variables, and the indicators themselves as being akin to dependent variables, if you want to think about it more from that type of framework. So at any rate, all of these factor loadings, all of those are positive and significant within this particular model right here. So you can see that you have tests of the standardized factor loadings themselves. When we scroll down a little bit further, now you can see that we have with our uniqueness values, now these would be interpreted as proportion of variation in the indicators that's not accounted for by the their respective latent factors. And then you'll see down here we've got the estimated variances for the latent factor. All of those have been fixed to 1. When we scroll down a little bit further, now these are going to be correlations, but correlations between the latent factors, and you still have your significance test for those. Okay, so now we can, if we want to, we can use some post-estimation commands to obtain measures of equation level goodness of fit and global goodness of fit. And so you can type those commands in the command line. Just for simplicity, I'm actually going to use the do file editor. So I'm going to go up here to where there's this little icon for new do file editor. I'm going to click on that and open up this box. And this is where I'm going to type my commands in and run my various analyses or post estimations and so forth. So what I'll do in this particular case is I'm going to type in ESTAT and then EQGOF, and that's referring to equation level goodness of fit. Let me also kind of increase the font just a bit here if I can. We'll just kind of zoom in a bit so you can get a better picture about what it looks like. All right, so if I highlight this and I click on execute selection, then you'll see that in my output, now I've got various measures of fit with respect to kind of the associations between the latent factors and their respective indicators. So as you're looking at this, you'll see that we have this column that contains R² values, okay? So that the values for all of these indicator variables right here, these are essentially communalities, and they reflect a proportion of variation in each of the indicator variables that's accounted for by their respective factors. So all of these values that you see right here, all of those are communalities. So as you can see too, looking at the values, all of those are quite high, indicating that the proposed factors are accounting for really substantial proportions of variation in the indicator variables. Now, if we go back to our do file editor, we can also use another post estimation command. I'm going to type in estat and then GOF, comma, and then I'm going to type in stats and then all inside parenthesis right here. And when I highlight this and run it, you'll see that we get global model fit statistics, all right, to evaluate the overall fit of our one factor model. So as you can see, looking at our output, we've got up here, we've got the chi-square goodness of fit test that's given, which is testing the exact fit hypothesis. So the null hypothesis for that, that test is that the sample covariance matrix and the covariance matrix that's implied by our model, that they are the same. In other words, they overlap in their elements, and that they don't differ. So if we reject the null hypothesis, in this case, we're actually, that would be regarded as an indication of lack of fit. So the significance, the chi-square test value is 82.97, and the p-value is 0.001. So that was, at least based on that test alone, that would be an indication of lack of fit. But we also know that the chi-square test is affected by sample size, and even small discrepancies between those two matrices could translate into, could still be regarded as indicating you could still end up with statistical significance because the test is overpowered due to the sample size. So we have that one test right here. The other thing to note too is that, in terms of our degrees of freedom for the model, there it is, the 48 that I was showing you earlier on. And the chi-square value itself, when you're looking at chi-square, essentially, if you have a fully saturated model, one that kind of fits exactly, your chi-square value would be 0. But then, as the chi-square value gets larger, then that would reflect greater discrepancy. So this value that you see right here of 82.97, we're going to be using that later on when we are testing the difference in fit between our first order factor model and our second order factor model. So in terms of the RMSEA right here, you can see that we have a value of 0.052, basically values that fall between 0 and 0.05 would be regarded as indicating close fit. Values between 0.05 and 0.08 are still regarded as acceptable. Values between 0.08 and 0.10 might be regarded as kind of mediocre fit. And then values above 0.10 would be regarded as poor fit. So looking at this, you can see that this kind of places us pretty near that close fit category. In terms of the this p-close test right here, it's 0.423. This is a p-value. Basically, we're testing whether our RMSEA that we have obtained in our sample data is it significantly different from what we would expect if the in the population we had close fit. And so in this case, you can see that the p-value is non-significant at the conventional 0.05 level. And so that's actually regarded as an indication of close fit. So if we had significance, that would be regarded as an indication of lack of close fit. But keep in mind the terminology here. We've got close fit, and then we've got, a model that is acceptable. So just kind of keep in mind those differences in terminology right there. We know that, again, based on our RMSEA and p-close tests, both of those are generally signaling that our model is not really different from what we might expect with a close fitting model. So in terms of the baseline comparison down here, you've got the CFI and TLI values, and so these fit indices are essentially representing comparisons between our model and a model where essentially the relationships among the variables are zero, reflecting no relationships. So these indices range between 0 and 1. The closer you are to 1, the better in terms of representing fit. And values that are greater than 0.90 are typically regarded as indicating acceptable fit. When you get up into the 0.95s or above, that's going to represent kind of more superior levels of fit or optimal levels of fit. So both of these values are indicating a very good fitting model right there. And then with the SRMR, we have this value right here, the 0.017. Basically, this is just another measure of goodness of fit. Values, if you have a value of 0, that's indicating a perfect fit of the model to the data. Up until about 0.05 might be regarded as good. Values between 0.05 to 0.10 might be regarded as acceptable. So at any rate, as we're looking at these values, you can see that overall, these are suggesting a quite good fitting model to the data. So then the next step in all of this is going to be to go back and respecify our model in the form of our second order factor model. So to do that, we're going to go back into our diagrammer. So we'll go back to, let me see, I think I've already got it up here. So here's the original model. So what I'm going to do is take a second here. There's clearing the estimates for you. I'm going to go back and respecify this model with a second order factor model, and then we'll kind of proceed from there. So I'm going to pause this for a second, and then we'll move on. Okay, so here I've respecified the model. As we talked about before, really the first order components linking the first order factors and their respective indicators, all that's basically the same thing as we had before, but now we have the second order factors with arrows drawn from them to the first order factors. And we have those fixed factor loadings of 1 in that structural portion of the model. All of the first order factors also have error terms associated with that, reflecting variation in those first order factors that's not accounted for by the second order factors. So at this point, we're going to go ahead and estimate the model. I'm going to go up to estimation, estimate as before. You'll see that under reporting, I've got it set for display standardized coefficients. We're just going to leave it set for that right now, and we'll go ahead and click on OK. And so now we have our fully standardized model. And as we're looking at it, just keep in mind that in our fully standardized model, this is going to be the correlation between the two second order factors. It's about a 0.3. You can see that we have our standardized factor loadings right here in terms of the first order factors with respect to the second order factors. So those are the estimates right there. And then we have our estimates in terms of the relationships between our indicator variables, our measured variables, and those first order factors in this portion of our path diagram. So next, what we'll do is we'll go ahead and open up, go back to the main output right here, just to kind of take a look at it. So as we do this, we'll kind of scroll up right here and go through the different portions. So you'll notice that first off, in our output, you'll see once, we've got this is referring to the standardized estimates. We have our coefficients right here. And so you'll notice it says structural right here. So these are the structural relations between our first order factors and our second order factors. So you'll notice that in this case, we've got the problems focused second order factors, the relationships between them, and the first order factors of problem solving and cognitive restructuring. These right here are going to be the standardized loadings right here. You can see both of those are positive, and we have statistical significance for both of those. In terms of the second order factors of emotion focused coping right there, we've got express emotion, and social support. Those are the first order factors with their respective associations right here. and both of those test results are significant. Then if we scroll down a little bit further, you can see that we've got the measurement portion linking the indicator variables to their respective first order factors. And basically all of these loadings that you see right here in that first column within this model are going to be correlations between the indicators and the higher order factors. So basically, these are all in this portion of our output right here. These values that are shown right here are going to link the indicator variables to their respective first order factors. And then in the structural portion right here, we're linking the first order kind of indicators, if you will, latent variable indicators in relation to the second order factor. But so all of those are going to be correlations in this particular model. As we scroll down, you can see that we've got, in this particular case, we've got our measurement errors associated with each of our indicator variables in the first first order portion of the model. So these are all the variances for the uniqueness values associated with those indicator variables. Then we have the variances for the errors associated with the first order factors right there. So you can see that how this is denoted with E dot and then problem solving, E dot cognitive restructuring, and so forth. And then in our fully standardized solution right here, we would also have the fixed the variances of the second order factors that are fixed to 1 right here. And then we've got the correlation between the two second order factors, as well as we have our significance test. So we have significant correlation of 0.301 for those second order factors. So we can also go ahead and request those fit indices and so forth. So if we go back, you can see here's our do file editor. We can type in, again, stick with ESTAT EQGOF for the equation level goodness of fit right here. So now you can see that with our R squared values right here, let me see if I can highlight this. We've got the R squared values associated with our indicators. So these values right here are basically reflecting the proportion of variation in the indicators that's accounted for by the first order factors. And then down here, we've got the proportion of variance accounted for in those first order factors that's accounted for by the second order factors. So you can see all those numbers are quite high. And in particular, as we look at those second order factors, those R squares range between about 0.66 to 0.68. So those are pretty nice values as well. If we go ahead and highlight this right here, ESTAT GOF, stats all, then run this analysis here, we've got our model fit statistics. So as we're looking at this, you can see the chi-square goodness of fit test right here. We still have statistical significance. You'll notice that the degrees of freedom is now 49, which is what we had talked about earlier when we were computing it. You'll notice that the chi-square value right here is going to be a little bit higher, or in this case is a little bit higher than the chi-square value associated with the previous model. And that would be expected, because what we've done is we've actually made our model more parsimonious. Because we're estimating fewer parameters, the number of the degrees of freedom of the model is actually increasing. And oftentimes then we're going to also see a chi-square value that's going to increase as well. So the first order factor model estimated more parameters. We essentially had fewer degrees of freedom, and the model in general, we would expect it's going to fit better than the second order model. Ultimately, the question is going to be, by specifying a more parsimonious model, do we sacrifice a lot with respect to fit? So in other words, does it make more sense to stick with the first order model that's less parsimonious, or does it make more sense to stick with the second order factor model that may fit a little bit worse, but then is also more parsimonious? And if the difference in those chi-square values is significant, then that would suggest maybe sticking with the first order order factor model. But if the difference is not significant, then we would expect then in that case that the second order model would be preferred, because it would be, you would be estimating fewer parameters. It's less complicated model. So we aren't quite there yet, but that's where this is going ultimately in terms of using these chi-square values from the two models. But at any rate, as we're looking at this, the chi-square test right here for this particular model, we have statistical significance, which we would reject the exact fit hypothesis. When we look at the RMSEA, we see that the value is 0.05. It's actually a little bit better in this case than the previous model. This is consistent with close fit. The p-close test is also consistent with close fit. When we look at the CFI and TLI right here, both of these values are indicating a very good fit of the model to the data. And then when we look at the SRMR, we see, once again, we have a very good fit of our model to the data. So at this point, we've looked at both of these models. They really both seem to largely be doing the same amount of, be doing the same thing in terms of fit of the models to the data. So then we want to be able to compare the two models to make a decision. Again, does it make more sense to stick with the less parsimonious model that might fit a little bit better in relation to the data, or does it make more sense to stick with the more parsimonious model that might fit maybe a little bit worse than the first order factor model? And so in this particular case, this is where we would carry out a chi-square difference test between the two models. So essentially what we're doing is we're taking the chi-square value for the second order model and subtracting the chi-square value from the first order model. We'll take the difference in the degrees of freedom there, and then we essentially perform a chi-square difference test using a command, basically a likelihood ratio test command using Stata. So we don't actually have to manually do this. There's actually a way to do this in Stata that is much less painful than having to sit down and compute everything by hand. And to tell you the truth, it's not actually that painful to do it by hand, but why do it by hand if you can automate it? So now what I'm going to need to do is actually to go back. I should have done this before. I'm going to go back to the first order model. This is it right here. I've just gone ahead and saved it. So here's our first order model right here. Just kind of, I'll shrink it a little bit so you can see it. There's our first order model. So I'm going to re-estimate and then get those goodness of fit statistics. And then I'm going to store the estimates from this model into an object, and then we will do the same thing for the second order model. So I'm just going to go ahead and click on OK, and we've estimated the model. And going back in here right here, you can see I don't really need this again right here, the the equation level goodness of fit. What I need is the overall goodness of fit measure. So I'll click on the button right there to run the model. And so you can see this is from the first order model. We had our 48 degrees of freedom. And there's our chi-square value. So once again, this is smaller than the chi-square value from our second model. So at this point, what I'll do is, now that I've estimated this particular model, I'm going to and generated the overall goodness of fit values, I'm going to type in estimates store, and you can type this into the command line directly as well. I'm going to call it M1. So I'm basically going to save all of the estimates from this particular model, which incorporates the chi-square value. So I'll type in estimates store M1. So when I highlight this and I run it, now those estimates are stored. Now, the next thing I'll do is I'm going to do the same thing with our second order factor model. And I probably could have been more efficient at doing this because I could have already done this earlier, but I'll re-estimate this as well. And as we're looking at this, you can see our output. We have the output from that particular model. So for this one right here, then I'm going to type in just estat GOF stats all right here, and then I'm going to type in estimates store M2. So that will be, so I'm creating another object that's called M2. That's for the second model, which is our second order factor model. So now I will click on execute selection and run that. So now we have the estimate stored for that second model. Now we can carry out the actual likelihood ratio test. So I'll type in lrtest for LR test, and then I'll type in M1 space M2. And so when I highlight this and run it, then I get a likelihood ratio test, which involves testing the difference between those two models. And you'll notice basically we've got this this little assumption here about nesting right there. You'll notice that we've got the likelihood ratio value, which is 0.03. If I take the value associated with our more restrictive model, with that value being 83.005, and I subtract the chi-square value for the less restrictive model, which is the 82.97. In that case, then our difference value is 0.03. So, and that would be used in carrying out the test. You'll notice that for this test, we have a 1 degree of freedom right here. And that's just basically reflecting the fact that we are, we had degrees of freedom for each of the models. We had our less restrictive model had degrees of freedom of 48. Our more restrictive model had degrees of freedom of 49. So the difference in those degrees of freedom is 1. And so then the actual p-value for testing the difference is 0.85. So what that's telling us is that there's not really a significant difference between the two models in terms of their fit. And so that would support or lend support for adopting the second order factor model because, again, it is a more parsimonious representation of the relationships among our indicator variables than the first order factor model. One other thing that I want to highlight is that, with these the chi-square tests, that's one way to test for the difference between our two models. But another way that we could talk about the difference in fit is by looking at the information criteria associated with the two models. So right here, we've got Akaike's information criteria, or AIC, and Bayesian information criterion right here, which are BIC. So these indices can be used to compare different models in terms of their fit and make a decision about which model is a better fit to the data. So keep in mind that these kind of account for both fit and parsimony of our models. And these were really developed more for the purpose of comparing non-nested models, but it works the same with nested models as we have in our current example. So if we look at the values we've got for our, we'll just kind of write this out right here for, we'll just call it our restrictive model. I'll just say restrictive second order model. Our AIC is equal to 11,343.637, and BIC for this model is equal to 11,448.524. Okay, so we've got those numbers, and if we what we'll do now is kind of scroll up and look at those values for the less restrictive model, which was our four-factor first order four-factor model. It's easy to get tongue-tied as you go through all this. But now, as we're looking at this, you can see that the AIC for the first order model is 11,345. That number is less than this number, or excuse me, is greater than the AIC for the second order model. And you can also see that the BIC for this model, 11,454, is greater than the BIC for the second order model. And so basically, when it comes to comparing models, you can't use the AIC and BIC to evaluate the fit of a single model. It doesn't work. But you can use these for comparative purposes. And so essentially, for both of these indices, the preferred model, if I have two models, the preferred model is going to be the one that would have the smaller AIC or the smaller BIC. So in this case right here, both of these indices are smaller with our second order factor model. So that lends additional support for adopting the second order factor model over the first order factor model. Now, these indices don't always necessarily agree, but in this current case, they both do agree in terms of which model would be preferred. So now, as we've gone through all this, you can see we've gone through the various steps of testing out a first order model, a second order model, and making the comparison between them. And so, based on our chi-square difference test, and also looking at the AIC and BIC, all of these this information would lend support for adopting the second order factor model over the first order factor model. So that's going to wrap up this video demonstration, and I appreciate you watching.